Determinant. This part is from section 3.1 and 3.2. We introduce determinants, one of the most important concepts in the linear algebra. So after finishing this lecture, you're able to compute the determinant of any squared matrix. But this does not mean your computation is the fastest way. So in the next lecture, we are planning to give some other properties which can make the computation easier. So we start with a question, why determinant? Why is it that important? So for a square matrix A, one of the common questions is A invertible? So before we said if A, the square matrix, belongs to n by n matrix, then you can ask the question, is A invertible? So one possible answer is that if the pivots of A, the number of pivots of A is less than n, then it's singular, it's not invertible. So what you do is you want to change A into its REF form and count the number of pivots. If this equals to n, the number of row or the number of column, then you can say it's invertible. It's a good matrix. Otherwise, you have some free variables and there's some singular behaviors, which means not invertible. Now we have a second approach to identify if this is invertible or not. So given a square matrix, you can always compute determinant of A. If the determinant of A is not equal to 0, then A is invertible. If determinant of A equals 0, then A is singular. So this is if and only if. Another application of determinant of A is from geometry. So absolute value of determinant A represents the volume of parallelepiped spanned by the column vectors, parallelepiped objects. We're not going to emphasize this property. So in this class, we only test this part. So A is invertible if and only if determinant A is not equal to 0. Now we're going to look at computation or definition. So we start with smallest matrix we can compute. So 2 by 2 matrix. So A equals given by A, B, C, D, 4 numbers, 2 by 2. Then determinant of A is AD minus BC. So that means the product of this diagonal minus product of anti-diagonal. So in determinant of A from this formula, it could be positive or negative. It's not necessarily a positive number. So remark, determinant A could be a negative number less than 0. We first look at one example. So we have two vectors, 2 by 1 matrix, 2, 2, and negative 1, 3. Draw a parallelogram formed by 4 points, 0, u, v, u plus v. So what is parallelogram? So we have u is 2, 2, v equals negative 1, 3. So both vector could be a point in two-dimensional space. So this is u, 2, 2, and v is negative 1, 3. This is u, this is negative 1, 3. And the parallelogram spanned by these two vectors can be considered as this object. Then what is the area of parallelogram? There are many ways you can compute this parallelogram. One example is if you know how to compute the area of a rectangle, then you can look at this big rectangle and then subtract those shaded triangles areas. So in this way you can try to find out the area. I will give it to you as one of the exercise after lecture. Now we're going to compute this area in a different way. So this parallelogram, the area in a different way using determinant. So the area of parallelogram is the same as absolute value of determinant of matrix UV. So what it means is U is given by 2, 2, V is given by negative 1, 3. So this is exercise by yourself. But using determinant, we can also compute that. So we do product of diagonal. We also do product of anti-diagonal and take the difference, which is 6 minus negative 2, which is 8. So the answer is 8. So show that the absolute value of determinant UV is equal to this area. So we are done. All right, now next we are going to prepare for the computation of 3 by 3 matrix. So to do that, we are going to introduce what we mean by minors of Aij. So if A is given by m matrix, this could be big square matrix, then the minor of given by Aij is in the m minus 1 times m minus 1 matrix, which is one dimension smaller. So let's look at the definition. For any square matrix A, let Aij denote the submatrix, which is smaller matrix, formed by deleting ith row, jth column of A. So for instance, there's 4 by 4 matrix, square matrix. Now, what is A sub 3 to? It's a submatrix. It's not a number. It's one dimension less square matrix, so 3 by 3 matrix, which is given by deleting third row and second column. So third row and second column, so 3 and 2. So if we delete these two row, this row and this column, then we get A3. Of course, we can ask different question. What about A23? Then what you do is you want to delete second row and third column, and the rest of numbers give you 3 by 3 matrix. So this is exercise. Now we can define the determinant of any m by m matrix. So for a given n greater than or equal to, the determinant of square matrix m by n square matrix is the sum of n terms of the form plus minus a1j determinant A1j, the minor, with plus and minus signs alternating, where the entries of A11, A12, A1n are from the first row of A. So the mathematical expression is for the determinant is equal to A11 determinant A11 minus A12 determinant A12 plus and minus plus minus all the way to the end. And you can also write this formula, this definition, using sigma notation, the summation notation. All right, just looking at this definition, it's not really clear. So we can look at one of the example and try to explain this definition. So what to do is, you can imagine there is a matrix, maybe 4x4 matrix, so for simplicity. Then you are going, this definition tells you to get the determinant, you are going to screen along the first row. So there's A11, A12, A13, A14. So, and then what you do is you want to put a sign to remind yourself in the computation, alternating signs to the first row. So I screened the first row and put the sign. Now we expand determinant. So the determinant is, so if you write down the determinant of this A, then it's going to be, so for this case, 4x4 case, it's going to be starting from this A11 and determinant of A11, which is 3x3 matrix. Then you take this, so because this is negative sign A12, determinant A12, and plus A13, determinant of A13, so that moves to here. And then the last term is negative A14, determinant of A14. And you, in other words, this is first step, but for 4x4 matrix, you still need to compute those determinant, which is 3x3. All right. Now we look at 3x3 matrix as an example. So A is given here. We first need to compute the determinant and then try to answer this question: is matrix invertible? The second question could be answered once you do REF of A and by counting the number of pivots. But we're going to use the result from determinant. So if the determinant is 0, then it's not invertible. So we're going to screen the first row, and I will put a sign plus minus plus. So the determinant of A is, I start from the first one, 1 times determinant of A11, and the second number, because the negative sign on top of 5, so 5 times determinant of A12, plus this 0 times determinant of A13. 0 times anything becomes 0. So this part can be ignored. But the first part is determinant of A11. So if I delete first row and first column, then the remaining 4 numbers are coming from here, which gives me 2x2 matrix. So 4, negative 1, negative 2, 0, minus 5. Now we look at the entry 5, which is, so you are going to delete the row and column containing this entry. Then the remaining numbers are given from 2, 0, negative 1, 0. So determinant 2, 0, negative 1, 0. Now for 2 by 2 matrix, the determinant is cross multiplication. So 4 times 0 minus negative 1 times negative 2, and 5. For its second determinant, 2 times 0 minus negative 1 times 0. At the end, so 0, negative 2. All right, so we have this answer for the first question. Now, is the matrix invertible? Because negative 2 is not equal to 0, so because determinant A is not equal to 0, A is invertible. All right, this is the end of the lecture. We stop here.